Hello, can you hear me? Hello, can you hear me? Dziękuję, Maciej, Zalewski, and Seseni Jinsenguo for organizing this fifth symposium on ecohydrology. My name is Karl Matthias Swanson. I'm holding a UNESCO chair on river culture, and I've been invited to talk about the water, energy, food ecosystem nexus. I would like to begin my talk with the name of Pierre Huguelin, who was an agronomer who studied the climatic conditions that are necessary to produce wine. Recently, a team of researchers has presented what happens to wine growing worldwide under climate change conditions. The results for Spain, the largest nation that is exporting wine, has been very sad. We had the situation that apparently wine growers cannot go on. But a colleague of mine, when I asked him the question about wine growing in future, he said, there is no problem. There can always be water deviated from the Rhone or Ebro rivers. And imagine how my French colleagues looked at him when he said this. So this phrase, there will always be water, needs to be questioned, and the question of water security has to be asked, for whom? There are multiple pressures, as you know from this Nature paper from Grill et al. We have an increasing number of people per landscape discharge in terms of surface, as evidenced by Michel Mebec. We have problems with specific types of agriculture, as the blood avocados in Mexico. The Cotaloniana, one of Europe's most diverse wetlands, is bored by illegal boreholes that make oblique water abstractions for strawberry productions. And near Strasbourg in the Upper Rhine, as soon as the farmers start irrigating their cornfields, the streams in the surroundings of the Grand Ried are falling dry and the fish get killed. So there are geopolitical water conflicts. There is a horizontal water cutting, for example, in the Kashmir region between Pakistan, India, and China. And we already heard this in the morning, transboundary, trans-basin river water transfer planned for saving Lake Chad, which has periodical higher and lower water levels, but possibly to the detriment of the Congo River by lowering its discharge. Huge amounts of carbon stored in wetlands could be mobilized. And we can look at it in the vertical dimension. Take the case of Kabul city in Afghanistan, for instance. We cannot dig deeper anymore. It's not only that the layers in the groundwater aquifers are lowering and lowering, it is also the water is getting colder and colder, which means that the refilling time of this water takes longer and longer as we are talking about older layers of groundwater. And vertical cutting can come from above, and this is the case in Amazonia, where deforestation is menacing the rainforest to be turned into a savanna, which would have detrimental effects on the biota and humanity. As we heard already in the morning by Andras Sölesnagi, the water connects everything to everything. I don't have to go into details of this, but I want to draw your attention that in SDG 6, the aspect of the ecosystem health comes last. Water sharing is a highly complex issue. Look at this graph here showing Greece's water, energy, food system under climate change and the necessary relationships in a paper by Ioannou and Laspidiou from this year. But the term ecosystem is still not considered. So the water, ecosystem, food, energy nexus, Wi-Fi seems to be a solution to get the ecosystem out of the vice that is pressuring the ecosystem due to the different uses. On the right, you see my favorite stream in Brazil, the Tenente Amaral, which I've been studying for 30 years now. And you see here how the nature is squeezed by the different use forms from all the directions, not only in the horizontal, but also in the vertical dimension. So transboundary basin management using this Wi-Fi approach is now promoted by United Nations Council for Economy in Europe, UNECE, and it is, so to say, a continuation of what we did before with integrated river basin management, which is locally criticized for being overly hydrological and not adapted to being scaled down or having social issues, or integrated water resource management, which has been criticized to focus too much just on water use. So this procedure that is proposed there by UNECE is composed by two different layers. The first one is an analytical one, more or less desk-based, including the different socio-economic contexts, the actors and the stakeholders, of course, and the different political and administrative sectors. And then in a series of iterative workshops to bring together these people into dialogues to develop joint solutions. So the added value of this approach is not so much the identification of single solutions, but rather the combination and coordination of actions. Let's take a closer look. And the Wi-Fi solution approach for UNECE includes 5 I's. The first one being the institutions that can establish cooperations and change possibly their governance culture. Here, the roles have to be clarified and the coherence has to be established. The information is a big issue, already mentioned several times in the earlier sessions in the morning. The accessibility and communication of data for monitoring and forecasting, the instruments being policy, legal, or economic instruments that can promote synergies and address trade-offs have to be harmonized and brought together across boundaries. And finally, joint efforts to be taken in financial or institutional support for infrastructure to increase the resource use efficiency or to optimize existing structures, and the international cooperation across boundaries and to share knowledge and develop common rules. An example for this transboundary cooperation is the Sava Basin in some countries of former Yugoslavia, where hydropower and water quality issues were very pressing, and where this approach could deliver integrated hydropower and renewable management and to protect floodplains and wetlands in a joint consultation process. Or the Northwest Sahara aquifer system in Northern Africa, where water pumping also translates into salination, into desertification, irrigation problems and energy problems are there that could be tackled with this Wi-Fi approach for a better use of the water in agriculture. The Nexogenesis project is a Horizon 2020 project with 4 case studies in Europe and 1 in Africa that wants to tackle the problems that still exist with the implementation of the water, energy, food ecosystem nexus. First, of course, we still have to deal with this complexity of this system, and especially with the integration of ecosystem, this ecosystem approach, which has not yet been sufficiently considered in the WEF system so far. The sectoral policy development, and to understand how these policies can interact with it. And the solutions that are coming along are a coherent policy-making framework at different scales. They use artificial intelligence to develop a self-learning engine and provide a Wi-Fi nexus footprint, not only a water footprint, but a footprint for all these four elements for decision taking. I would like to end my talk with a consideration of some things that are quite obvious, and some of them have already been mentioned in the morning. In first place, it is really population size and the trends. Here I would suggest a 25-35 approach to promote that humans should reproduce prioritarily in this age, which would mean that people have time for education before they start getting babies, and which would, as we see from many different demographic analysis, that this is really forward way. The other one is our consumption of meat, but also of other natural resources in general. Here, I would suggest to feed like water turtles. They are carnivorous as long as they are very small, and the more they grow, the more they go veggie and finally cease consuming meat. This could be a way how to introduce a more water sensitive diet for humans without being directly in confrontation with vegan or not. We have also to acknowledge the primacy of ecosystem functions. We had this in the previous talks by Martier, this transfer from this anthropocentric system to a more ecosystem centrum, and I would like to reinforce here the statement about the natural retentiveness, not by dams, but by the natural sponge capacity of the headwaters, and combined with a rewilding and mild use in especially headwaters to maintain the discharge. And we just had this presentation by Professor Mediondo, who showed how this can work. Business as usual is a killer, and we really need disruptive changes in some fields of society, agronomy, and economy. We cannot go on, like in the first example, to say there will always be water. No, we see that some areas are made unsuitable by climate change, so we have to abandon these areas, or at least give up certain forms of agriculture, and the people that migrate away from there need to be integrated. I have a critical view on SDG 6 and IHP 9. Non-humans also have water rights. This has already been mentioned, but as I said before, if ecosystems come in the 6th place out of 6, we still have some work to do. And finally, we see that along with biological diversity losses, we have also cultural losses, and we can learn to live with your river by studying how people have done this in a traditional way. We can learn nature-based solutions from organisms, and we can also be very inventive. And that is what I presented here with this recent book on river culture. This will appear very soon at UNESCO Publishing. Thank you very much for your attention. Okay, I cannot hear you. I stop sharing. I still cannot hear you. I see here a question. I read it aloud. From your presentation, I understand that you are well aware about transboundary water management problems. My issue is the Nile River. The Nile River water is a sensitive issue causing instability in East Africa and ... Yeah, affects your country in Ethiopia. Yeah, this is a big issue, and in the river culture concept, I have brought up this idea of a bassin de responsabilité, which means that all people living in one river basin should be considered as one political unit that takes the decision together about the water use. Because currently we are dissociating the impact at one side and the bargain or the revenue from disturbing nature or even destroying nature on the other hand. And these people have to be brought together. I still have no acoustics here. I do not know if you can hear me or if I can hear you. Don't know what's going on. Are there further questions? Otherwise, I would pass the word to the next speaker. Time is over.
Water resources in the face of global climate change became one of the critical environmental factor. It's not working. Oh, okay. And we know that global climate change is a crucial element. So last 10,000 years was very kind for modern human civilization, because we had only 1 Celsius degree plus and minus. And now we know that we are moving out from Holocene and we are going to the planetary boundaries. We exceed planetary boundaries, and we will go to anthropogenic Anthropocene. So we can say that we live on a big world and at a small planet. It's not working. Okay. You know, more people, more water use. So global fresh water use is as essential as estimated at 4,000 cubic kilometers per per year. And here you can see types of human interference with the global water cycle and dimensions of global global water crisis. So scientists, sorry, back again. It's not working. Oh. Okay, so scientists are nervous, very nervous, because we are a situation where maybe we exceed very very important planetary boundaries, and the increase of temperature on Earth intensified the global water cycle, and in consequence increase also the frequency and frequency of extreme water phenomena like drought, like floods, wildfires, and storms. According Economist Report 2022, 44 countries face either extremely high or high water stress level by 2040. And additionally, for example, European waters getting cleaner, but big challenges remain. And here you can see the map with the map proportions presents the proportion of surface water bodies in less than good ecological status according to Water Framework Directive norms. As of course, as water is extracted and used along the supply chain, both the quality and quantity of water is reduced. Of course, we have 17 development goals, especially four goals. These goals are like roadmap for achieving sustainable and safe future, but we must remember that economy should be seen as a mean to achieve social goals and generating prosperity within the limits of the earth, but not as an end in itself. For achieving sustainable development goals, we need transformative changes, and because they are necessary for regulation of processes, we need innovation, solutions, new ideas, new paradigms, circular economy and ecohydrology solutions, and also nature-based solutions. Which we can combine with a conventional infrastructure to improve water, biodiversity, ecosystem services, resilience, culture, and education benefits. Here you can see our example. We need more water in the landscape. This is a crucial element, because this is crucial element of the landscape. Therefore, like you can see, the aim of our research was to demonstrate how ecohydrological nature-based solution can be combined with conventional infrastructure to improve many benefits. And here you can see two examples of reservoirs, one hydrotechnical and second multifunctional ecohydrological variant of the reservoir. And in this reservoir, this is our proposition, in this reservoir will be supplied with water during periods of good water quality in the river through the monitoring and regulatory system. And second, the reservoir will have biofiltration system on the inflow part of water to the reservoir. Of course, the concept of this multifunctional reservoir was developed on the basis of detailed analyses which were carried out for 4 years. This reservoir, this example is important because lateral reservoirs increase water retentiveness, like you can see in the river valley, by lifting groundwater level and restoring surrounding wetlands, thus enhancing biodiversity, ecosystem services for society and the resilience in the face to climate change. Here you can see our experience with analysis of the Baltic Sea situation, and we have general question: why is the hierarchy of factors exerting an impact on nutrient load of the Baltic Sea? And our analysis showed, and now we know which are the crucial points for Baltic supplying of with nutrients. Of course, we also know which countries are the biggest supplier of pollutants. Here you can see our experience, ecohydrological quantification of the outflow of nutrients from wastewater treatment plants, and how this wastewater inflow to quality of water in the Pilica River and also in the Vistula River. And it's not, we have not good situation with dioxins and PCBs, because our analysis show that our wastewater treatment plants have also problem with these parameters. And here you can see analyzes the impact of wastewater treatment plant size and sampling season on the prevalence of antibiotic resistance genes in wastewater and in river water. And our studies show that in all wastewater and river water samples we find antibiotic resistance bacteria and genes. Another analysis was to assess the sanitary conditions of treated wastewater and river water based on fecal indicators and carbapenem-resistant bacteria. And our analysis show that these bacteria were found in the effluent of all tested municipal wastewater treatment plants, and also in the rivers. So this is not good information for us. So the big data we try to analyze by using of the Cohen artificial neural networks to analyze the catchment processes. But also, quantification of process is important, but we also try to develop some solutions. And here you can see example of nature-based solution dedicated for small wastewater treatment plants. This is a hybrid sequential biofiltration system, which is located in the Rozprza town. This system was working in good efficiency. Now we start to construct another bigger system, bigger sequential biofiltration system in Shadek. This is also example of nature-based solutions. And then I would like to tell you about also some good information that natural river floodplain have also a huge potential to retention of pollutants and self-purification. For example, during the flood processes and sedimentation at the floodplain river. And we also have important tool to river purification by using floodplain as place where accumulation of phosphorus and other pollutants can be obtained by plant tissues. My projects, and at the end I would like to thank you, my colleague, for cooperation. Thank you.
Thanks, Edita, for the nice presentation. I would like to open for question, if any, for her. Any question? No? Okay, then maybe we can continue to the next presentation.
Okay, so now I would like to invite Professor Tatiana Solowej from Polish Geological Institute, National Research Institute from Warsaw. Tatiana, please.
Good morning, ladies and gentlemen. It is my great pleasure to meet all of you today. I would like to tell you a few words about our achievement in scope in transboundary groundwater monitoring that we achieved in the EU WaterS project. Groundwater is a difficult object of monitoring studies because, firstly, sampling is possible after making a borehole. Secondly, their spatial distribution is unknown, and without research, their occurrence cannot be determined. Another important issue, but typical for all natural objects, is that state borders do not exist for them. They are only for people. So, when thinking about transboundary groundwater monitoring as a tool for controlling transboundary impacts, we must remember that the flow can occur along the entire border. How to deal with this situation? The easiest way. You need to determine whether the state border crosses the groundwater catchment. That is, if so, as shown in figure A, monitoring is essential. If the border runs along the river, which is the border of the groundwater balance unit, there is no need in cross-border monitoring, but to determine it, a balance sheet survey may be performed because there may be hidden surprise, as shown in figure B, where for useful aquifer, the river is not the balance limit and monitoring is essential. In this monitoring, we focus on tracking the effects of interconnections on the transboundary hydrological system in natural and anthropogenically changed conditions in order to prevent the development of adverse transboundary impacts. It is not only about controlling anthropogenically induced processes, but also natural changes, such as the impact of lowering the drainage base and climate change. The main task of cross-border monitoring is to provide information about the direction and intensity of the transboundary groundwater flow, compliance with the conditions for sustainable abstraction of common groundwater resources, and cross-border migration of pollutants. And the most important thing is that no matter how extensive the national monitoring is, it is impossible to assess common resources, plan their sustainable collection and corrective measurement without the data of cross-border monitoring. There is currently no cross-border groundwater monitoring network on the Polish-Ukrainian border. The concept of its creation was initiated by us in the EU Water-S project. The condition for this was the fact that the border in most of the section doesn't run along natural barriers to the flow of groundwater. We are dealing here with three large groundwater balance units, which were defined by us after the hydrological data were merged with the Ukrainian side. The first unit is located within the Bug Basin, in second in the San Basin, and the third in the Dniester. The presented research area is characterized by very difficult hydrological conditions because it is located at the junction of two geostructures, the East European platform and the Carpathians. As far as the relief is concerned, it is quite diversified, starting with the Mersey Plain in north through the Wolynskie and Rostocze uplands and ending with the Carpathian Flysch region in the south. The complex hydrological conditions in the Polish-Ukrainian border are affected by significant anthropopressure caused mainly by the presence of sulfur depleted areas and both sites in the sun catchment, coal mining areas in Ukraine. To these main threats, one must add the typical anthropopressure associated with groundwater abstraction, intensive agriculture, and urbanization. Now I would like to discuss our concept of creating cross-border monitoring, which we developed and tested in the EU Water-S project. We distinguish 7 stages justifying the need for this monitoring: data harmonization, creating a hydrodynamic model, designing a cross-border network, assessing the suitability of national network points, harmonizing methodologies for field measurements and lab tests, and developing criteria and methods for assessing transboundary impacts. The characterization of transboundary aquifers are mainly conditions the transboundary monitoring. The basis tools are the transboundary hydrogeologic cross-section, with which we had clear evidence that transboundary flow occur not only in shallow quarterly layers that are very important for water-dependent ecosystems, but also in deeper useful horizons. Miocene in the Sun Basin and Cretaceous in the Bug Basin. In the border area of the Dniester catchment, most of the area is devoid of useful aquifer, and the transboundary flow occurs mainly through rivers. Detailed recognition of the cross-border layers was only possible after harmonizing and merging the data. We have developed a common GIS database consist of 16 information layers, which can be viewed on our geoportal. I encourage you to use this data because you will not find similar information anywhere else. In the next step, a hydrodynamic model is necessary to calculate the intensity of the transboundary flow. The main role is to properly tar the model and rely on natural boundaries conditions. By defining the boundaries of the model, we identify the area significant from the point of view of the transboundary exchange of groundwater. The model boundary is shown in red on the map, as can be seen in Zone A, where the Bug is the state border. Cross-border flows are impossible due to drainage role of the river. Below in Zone B, there is a flow of groundwater in usable levels, mainly towards Ukraine. In Zone C, in the Sun catchment, the flow is directed to Poland. The created model is regional and consists of two wires with unconfined and confined groundwater tables remaining in hydraulic contact. In the concept of the water balance, it was assumed that its possible site consists of infiltration feeding. The negative components of balance are evapotranspiration, runoff, and groundwater abstraction. The analysis of the parameters of the model results showed that more than 1.5 times more groundwater flow from Poland to Ukraine than from Ukraine to Poland. The groundwater balance shows that the uptake of groundwater is negligible and amount to 3% of the TBA's supply. Based on the model, we defined the trajectories of transboundary flows and defined the area of interconnection of the hydrological system. On the present maps, separately for two catchment, the red hatch shows this area in natural conditions. We put objects of potential threats on this area. We locate points on cross-border transit that start at the site of potential threat and reach the local drainage base. On the other hand, in areas without anthropopressure, priority is given to a system where the supply zone is in one country and the drainage zone is in another. Then we allocate at least 1 point in each zone. It must not be forgotten that each country has well-functioning national networks, and this potential should be exploited. Our portal provides information on all monitoring points in the border area and present the results of groundwater table measurements and water quality assessment. But not all of these points can be used for cross-border monitoring purposes. Having the model and assumptions for the organization of this network, we verify the suitability of these points for the target network. Target network. Only 16 out of 58 border points of national networks of Ukraine meet the requirements of cross-border monitoring. In Poland, out of 30 points in the border area, only six qualified for the cross-border network. In the slide, green marks the 7 areas where the Ukrainian side intends to locate new points according to the assumptions of the transboundary network. The table contains information on which aquifer should be monitored. The next steps should concern the harmonization of methodology for field measurements and lab tests. The key is to agree on the scope of monitoring indicators, frequency of measurements and tests, and to use reference method which will allow to obtain comparable results. The most difficult part of the conception of cross-border monitoring is the criteria and the way to interpret the results. That is the assessment of transboundary impact. The example shown in the slide concerns only one aspect, the assessment of the impact of the current and maximum permitted groundwater exploitation on the condition of the hydrological system. As you can see, exploitation on the current level doesn't cause cross-border capture of resources, but if each party reaches the maximum abstraction rate allowed in their country, we will deal with interstate and intercatchment resource capture. The criteria and the method of assessing the transboundary impacts in terms of quality are so far agreed between partners, and we are currently working on creating a model for the migration pollutants. To sum up, the most important outcome if our works in EU Water project is the development and design of a transboundary monitoring network. This design was based on many factors like data harmonization, numerical modeling, analysis of the current field and lab procedures, analysis of already existing national monitoring networks, and many others. Thank you for attention.
Okay. Thank you, Tatiana, for interesting presentation about transboundary groundwater sources. And now,
Okay, supposedly we have a next presentation by Johannes and also Deng Hua, but unfortunately they are not available. They are not there. So we will go directly to the last presenter for this session, which is Professor William Mitch from the Ohio State University Everglades Wetland Research Park, and chair for Southwest Florida Habitat Restoration in Florida. He will be presented on nature-based solution and ecological engineering, our best hope for restoring lakes, river, and estuaries, and protected human health. So please welcome Professor William Mitch.
I would.
Yes. Can you hear me?
Yes.
Okay.
I would like to add only that Professor is a winner of the Stockholm Water Prize. So, Professor, the floor is yours.
Okay, well, thank you for the welcome, and I will try to give my talk shortly so that you can have a ample lunch break. I'm going to be talking about nature-based solutions and ecological engineering because, quite frankly, I think they're the same thing. And then I will go into some examples of both situations where nature-based solutions are being used in Florida, in the Florida Everglades especially. And I do believe that if they are the same thing, we have to come to some understanding of when you use nature-based solutions and when we use the term ecological engineering. Next slide. Well, this is a big summary of the history of NBS, nature-based solutions. They in a editorial, and I was a co-author on it, published in the new journal called Nature-Based Solutions. It's a new Elsevier journal. They suggested that NBS synthesizes ideas from the following, from in the pursuit of sustainability. And the first point they bring up is ecological engineering. Then they also say it's natural capital, green and blue infrastructure, and ecosystem services. So it's all the above. Now, what you have to understand is that we invented ecological engineering. So I'm trying to compare NBS to ecological engineering. We wrote the book in 1989, we being me and Professor Sven-Erik Jørgensen from Copenhagen. And then we redid a book on ecological engineering in 2004. And I was editor-in-chief of the journal Ecological Engineering, another Elsevier publication, for 25 years in the 1990s and 2000s. So ecological engineering was described by us as the design of sustainable ecosystems that integrate human society with its natural environment for the benefit of both. That was published in the 2004 book by Sven-Erik and me. Nature-based solutions describes their system as building with nature and for nature, which I think is lovely, and it's very precise. But it's pretty much the same thing, very similar in context and so on to the ecological engineering. So I'm just proposing to you all that nature-based solutions has actually been around for 40 years. When we first started exploring where ecological engineering was, I realized that scientists are afraid of the word engineer. That is one of the main reasons they have a new term, but they shouldn't be, because we are engineering landscapes when we are doing nature-based solutions. So I propose that we somehow move on and use both terms accordingly, but that we understand they are pretty much the same thing. It will be interesting to see how the new journal called Nature-Based Solutions develops and how it's contrasts from the current ecological engineering journal, which is very robust. So next slide, please. So I have two examples in the beginning of my talk here on what is ecological or nature-based solutions that I consider nature-based solution and what is not. This is a river that was Kissimmee River flows into Lake Okeechobee at the head of the Florida Everglades in south central Florida. And you can see that they straightened the river in the 1950s at enormous cost. And then they decided that was stupid, which we could have told them then if we were around. And then they decided they wanted to restore the river. So they went back to the original curves and copied the river, if you will, and re-meandered the Kissimmee River that now still flows into Lake Okeechobee, but takes twice as long to get there. To me, this is absolutely copying nature. This is a nature-based solution. We knew what the river used to do. It was still engraved in the soil, if you will. And so it was very easy for the scientists and engineers to put the river back where it used to be. So I have no problem with calling this nature-based solution. Next slide. This is not nature-based solutions and is actually a $2 billion restoration that they're proposing to do in the Everglades that is very strange. We don't understand it, where they're building a 10-meter tall embankment to hold back about 8-meter tall water height in a reservoir. And the Army Corps of Engineers, U.S. Army Corps of Engineers, drew this diagram. All we did was copy it for my slide. And it is not anything even remotely close to what nature does in the Everglades. We don't have volcanoes there that can create big walls like this. So it's bound to fail. And I've told them that. And I'm telling them they're wasting $2 billion. And ironically, in Florida, I am a minority on that. Most of the environmentalists and so on want this project, not because it's going to solve the problem, but because it's $2 billion coming to the economy of Florida. I'm not kidding that. I could talk for this all day, but it's going to be an absolute disaster. Next slide. So here's the area we're talking about. We're talking about South Florida, and there's all sorts of issues. That the Greater Everglades is a system of rivers, overflowing lakes, and then ultimately the water goes to the sea. The first graphic is historically how the Florida Everglades was created as a slow-flowing outflow from Lake Okeechobee, which is the headwaters. The middle graph shows what we're doing now, which is wasting massive amounts of fresh water, sending it to the Gulf of Mexico to the left, and sending it to the Atlantic Ocean to the right. That's where all the water goes. It pollutes the estuaries on both coasts. It does no good for anything, and it's required because of the legal issues related to flooding upstream if they don't throw the water somewhere. The right-hand side, which is a dream right now because of so many conflicting interests and projects, that they want the water, we all want the water to go north to south and end up in the estuaries to the south. That's where it's needed. That's where the prime part of the Everglades is. It's sometimes called the River of Grass, even though it's not grass, it's a sedge. And I think it's a daydream because I think they're wasting billions of dollars on things like what I show in the middle graph here and what I showed in the previous thing, which they haven't even built yet. Next slide. This has too many words, but this is what this shows, though, is in 2016, a very unexpected situation. This is that Lake Okeechobee dumping its water into the Gulf of Mexico. So this is one of those big flows that goes down and hangs a right, if you will, and goes into the Gulf of Mexico. And that is not a parking lot that you see under the text. That is the absolute water coming out of Lake Okeechobee and going into the beautiful green-blue Gulf of Mexico. This absolutely shocked people when this happened in 2016. They couldn't believe it. It changed the narrative entirely. And it happened in February, which is usually a dry season. We have a dry season and a wet season in Florida, and this was the dry season. And it wasn't supposed to be raining, and there were rains, and they claimed that it were probably due to excessive amounts of rainfall, probably caused by El Nino. At least that's the speculation, that this was an El Nino effect with a very wet, dry season, and it's what caused this dirty water. It's not, it looks like a oil slick, actually. It's not, it's just dark tannin colored waters coming out of swamps and lakes and all sorts of aquatic systems and going into the crystal clear Gulf of Mexico. So this caught the attention of everybody in Florida. Next slide. And then 2 years later, in 2018, I don't know if any are familiar with what's called a red tide. It's in our case, it's a red algal cell that causes great harm to aquatic species. And in August of 2018, we had one of the worst cases of aquatic pollution and death of sea animals and fish and so on that I've never seen anything like this. This was on the Gulf of Mexico also, and it was due to the algal blooms caused by red tide. There were also blue-green algal blooms on the freshwater side, and combined, it was one of the worst pollutions that I've ever seen anywhere as far as loss of aquatic life. So these are the historic situations that caused everybody to realize they're not making progress on cleaning up water when episodes like this happen in South Florida on our beaches. Next slide. Well, there are ways to fix things with wetlands, and I guess that's my pitch to you. And in fact, you can see here on the graph that Lake Okeechobee that we've been referring to is up in the top there. Then the water flows south through the Everglades agriculture area. It is not natural Everglades at all. It is sugar farms mostly. And that water was then headed through the Everglades, which is way to the south. And at least for this, there was some activity, and 2,300 hectares of treatment wetlands were created. They were told not to call them wetlands, so they called them stormwater treatment areas. The lawyers get involved in these kind of silliness, but they were wetlands. They were treatment wetlands. And this is one of the largest masses of wetlands built in any location for cleaning up water, 20 or 23,000 hectares, and they work. Next slide. This is what they look like. They look like wetlands. Sometimes they're growing. I don't know if this is Tifa or we call it Typha, but this is what those stormwater treatment areas look like. Next slide. And this is the water quality. The blue line, look at the blue and the orange lines. The blue lines are the inflow phosphorus concentrations, and the orange lines are the outflow total phosphorus concentrations. And they work enormously well. And some numbers are for 2015, 16, and 17 are below. They're really effective. But we still have this unofficial goal to get to 10 parts per billion of total phosphorus before it's allowed in the Everglades. They're close on this, but they haven't gotten exactly to that. And so anyhow, that's the goal, because that's the ambient water quality in the Everglades itself is about 10 parts per billion of total phosphorus. And that's what you have to assure that the Everglades is not going to be trashed with algal blooms as well. Next slide. And then there's a new ecological engineering approach. If I have time, I'll quickly go through it. We call it wetliculture, sustainable agriculture with wetlands. It has the word wetla for wetland and culture for agriculture. And we've been developing this approach for about the last 5 or 10 years. And next slide. This illustrates the box you see on the top in red illustrates the flow of nutrients through a typical agricultural landscape, where the fertilizer is applied to agriculture. It goes through the human economy, and the waste fertilizer and what's not used and so on goes downstream to lakes, rivers, and estuaries, and is the source of main pollution. We need to solve this problem. So we designed a system of wetliculture, which is shown in the circle in that same landscape below. And what it involves is agriculture putting treatment wetlands on the landscape in addition to the agriculture in the landscape, and thereby building a treatment system that takes the nutrients out of the water in the same landscape where we're growing crops, and recycles those nutrients back to aquaculture or to some productive system that can be used. Next slide, I'll show you. So what we see happening is that with pathways 1 and 2, sort of an internal cycling of nutrients, then the fertilizer industry won't be shut off, but it will be slowed down dramatically if we can recycle nutrients in the system rather than continue to put new nutrients on. The standard agriculture practice around the world is to just continue to fertilize, fertilize, fertilize. And we just can't afford to continue to do that. We're running out of fertilizers, number one, but we're also running out of the ability to do it cleanly without destroying downstream ecosystems. So this is a clean water and agricultural solution. Next slide. I'm going to quickly show you 3 examples of experiments. We did it at a mesocosm level. This one was done in Naples, Florida, constructed in 2018. And we actually planted the plant that is grown in the Everglades in these mesocosms. Next slide. This is one of the sites we had up in Ohio next to Lake Erie. Many of you know Lake Erie is in the Great Lakes, and it's very, very polluted by phosphorus. And we were looking for opportunities to see if the same wetliculture approach could be used up there. Next slide. These are just the numbers in micrograms per decimeter cubed, which basically is parts per million of total phosphorus going in and out of this wetliculture mesocosm you just saw in the previous slide, and very effective in both years. In fact, real effective in 2019 in taking 80 or 90% of the phosphorus out of the water. And next slide. And in another site we did in Ohio, this was done up in central Ohio, we were actually able to grow corn, a corn product, with those fertilizers that were captured by the wetlands. And that's the recycling that we just talked about. Next slide. And I asked my artist, let's draw what a landscape of wetliculture looks like. And she did a very nice job on that. You see the birds flying over, you see areas, and I don't even know which of these rectangles is agriculture and which is agriculture, but it's a mixed system that would clean up the water, but also protect downstream ecosystems and support lost habitat as well. Next slide. And we also, I don't have time to go over this, but we also have a professor from the University of Notre Dame helping us with a business model for this, whereby farmers could make money. The green arrows are flows of money, and you can see green arrows going down to the farmer. They get paid for producing clean water, and also they get grow crops that make money for them. And then also there's an idea that we could also have bonds that are, that people can invest in this, if you will, and make money investing to have clean water. It would take a half hour for me to describe this diagram, but it's a very exciting idea that this could be a very strong business model as well. Next slide. So I have some conclusions. I don't know if you can read it, so I better read them to you. Freshwater harmful algal blooms threaten aquatic life and human neurological systems and may become a health threat equal to our current pandemic. There are so many cases of illness, especially neurological diseases that are caused by algal blooms. I think we've only seen the tip of the surface on this health menace. Restored and created wetlands can remove significant amounts of nitrogen and phosphorus. And by the way, they can also take carbon out of the atmosphere. That's a wholly another advantage, that if you have a productive wetland, you're going to have productive carbon sequestration. And then the third thing is it's possible to clean up large nutrient pollution problems, such as the one I just told you, where we have 30,000 hectares, 20,000 hectares of wetlands that were built specifically to clean up water, and they work. So it can be done not on a few hectare size wetlands, it can be done on a very large scale, like the one we showed you in Florida. Next slide. Wetliculture could provide a sustainable business approach to lessen our fertilizer excesses. Farmers and investors could make a profit either by farming or creating wetlands, and downstream waters will be cleaner too. And then finally, one of my summary talks or summaries that I give on many of my talks, wetland restoration should follow the principles of ecological engineering and, according to what I read about it, nature-based solutions. They should be based on an appreciation of Mother Nature that's self-designed, that the nature is designing a system to help us. And also, Father Time, these ecosystems, when you create them, take time. They're not instant wetlands. Next slide. So thank you very much for your attention. And if you want any literature on what I just talked about, you have to be able to Google Everglades Wetland Research Park, and you'll find massive numbers of papers on this subject. So thank you very much.
Thank you so much, Professor William Mitch, for the very great and informative presentation on nature-based solution. What is nature-based solution and what are not nature-based solution implementation. So before we end this session, is there any question? No, because I think it is very all presentations are very unique and informative, and in fact, for example, I work on ecohydrology now, and I found many unique implementation of ecohydrology, for example, in groundwater, which currently I think we still don't have demo set that do ecohydrology on groundwater. So maybe it will be new dimension on how to implement ecohydrology in groundwater. Maybe next can become our ecohydrology demo site also. So that's, I mean, of course, we open for all to join our ecohydrology demonstration site. And I noticed also from the presentation have many implementation on ecohydrology, and will be good to join us next time. Okay, so Prof. Edita, maybe you want to add?
Yes, thank you, Elfiti. I also try to conclude. We generally we can say that we live on a human-dominated planet, putting unprecedented pressure on the system on Earth. Generally, this is bad news, but perhaps surprising for you, this is also part of the good news, because we are first generation, thanks to science, to be informed that may be undermining the stability and ability of the system on Earth. So we know what we should do. We know how we can do. So we just do. We should achieve sustainable future. Thank you. And now we would like to invite you to lunch.